Hi, well, I'm pleased to be with you here today, and I've been asked to talk a bit about the background and vision of Mathematica. You know, this month it's exactly 25 years since I started building Mathematica, and it's been really exciting seeing Mathematica grow and prosper over the years. But I have to say that in just the last few years, something truly remarkable seems to have been happening. It feels like Mathematica is really coming of age. It's in just the right place at just the right time, and it's making possible some fundamentally new and profoundly powerful things, like Wolfram Alpha and CDF, and yet other things that we'll have coming over the next year. But okay, let me start off at the beginning. How did Mathematica come to be in the first place? So here's the personal story. I started out in my teens as a physicist, and doing theoretical physics requires doing lots of mathematical calculation. And I figured these calculations are kind of mechanical. Why can't I just get a machine to do them? Well, that was in the mid-1970s, and at the time there were a number of research systems for doing algebra and things by computer, and I started using them and managed to do some pretty interesting physics with them. But it didn't take long for me to outgrow the systems that existed. So late in 1979, I decided that the only way I was going to have the kind of system that I wanted was to build it myself. So I did. And pretty soon, the system I built became the first commercial computer algebra system. But after a few years, I wanted much more. I mean, I'd been doing a lot of basic science, developing the foundations for what became known as complexity theory, and doing a lot of things that were really only made possible by computers. But it was kind of a mess. I had my nice computer algebra system, and I had programming languages and graphics systems and numerical subroutine libraries and typesetting systems. And I realized that actually I was probably spending most of my time just gluing these things together. So that got me thinking. Perhaps I should just build a single system, once and for all, that could do all the computational stuff I'll ever want to do. So I thought about it for a while, and then exactly 25 years ago this month, I decided that yes, I should do this. And I started building Mathematica. So right from the beginning, I had several principles. I suppose the first was very personal. I wanted Mathematica to be the only computational system I'd ever have to use in my life. So I wanted it to cover everything I'd ever want to do and to have a structure that was strong enough to extend as far as I wanted in any direction. I mean, I knew Mathematica would be a big system and would keep growing, and from the beginning I put incredible effort into making sure that it was coherent and unified and would always remain so. I wanted all the pieces of the system to fit perfectly together so that if you were using one part of the system, you'd immediately be able to pull in some other part and you'd immediately know how to use it, and it would just sort of fit seamlessly in. Then another principle, I wanted the system to be as automated as possible. I mean, the whole point of using a computer is to get it to do work for you. So the concept was that you should just tell Mathematica what you wanted to do and it should figure out how to do it. So if you were an expert, then you could set all sorts of knobs and switches, but most of the time you just let Mathematica figure out underneath the best algorithms for things or whatever, completely automatically, so that you as a human could get on with thinking about what you wanted to do, not telling the computer how exactly it was supposed to do it. Well, so those are the principles, but how should the system actually work? Well, there's a big idea there. It's symbolic programming. Actually, when I started working on the forerunner of Mathematica back 32 years ago, I guess I was kind of a dyed-in-the-wool young basic scientist, and so I figured that to make a system for doing computation, I better understand at the most fundamental possible level what computation really is and how it should be represented. And so I went back to the foundations and realized that there's a very clean way to do that. The key idea is that everything can be represented as a symbolic expression, whether it's a string, an array, a formula, a graphic, a program, a document, a user interface, whatever. And because everything is represented in a uniform way, there's a uniform set of operations that can be performed on it. And that's in effect how this giant system that is Mathematica can fit together so well and work in such a coherent way. I mean, it's funny, in a sense, symbolic programming is the secret that makes Mathematica possible. And when you start using Mathematica, it's something that's just there, sort of always providing a framework for what's going on. But I guess symbolic programming, to make it really work, as it does in Mathematica, is hard. It needs a big technology stack, which is why, even after all these years, serious symbolic programming is still pretty much a unique feature of Mathematica. Okay, so let's take an actual little look at Mathematica. There are many ways to use Mathematica. Here's one. You just type in a question, it prints back the answer. So let's say Let's say we type in 1000 factorial. Okay, there's the answer from Mathematica. Now let's say we ask Mathematica to plot a graph. Let's say plot sine x plus sine 10x with x going from 0 to 20. Okay, there's the plot. That was easy. Okay, so let's say we want to make that dynamic. Well, that's easy to do too. We just add a parameter here and then tell Mathematica we want to manipulate as a function of that parameter. Now you just change the parameter a and you can see this graph change. We just created a little user interface in just one line. Actually, you can manipulate anything. Like, let's manipulate a piece of algebra. And of course, because this is Mathematica, this just works. Well, okay, let's make some data. We could import the data from anywhere, or we could connect to some external device or program or whatever, but let's just make some data right here in Mathematica. And now let's say we want to interpret this data as a description of a network. We can ask Mathematica to plot that, and it'll automatically figure out a good layout. What if we want a bunch of these? We can just make a table. And Mathematica automatically laid out each of these networks. Or for example, we could arrange these in a bunch of tabs in a little interface. Or we could set them up with manipulate or whatever. You know, Mathematica can deal with pretty much any kind of data. Like, let's just get a picture from somewhere on the web. Let's just go ahead and drag that picture into Mathematica. There we go. Now, because this is Mathematica, we can just immediately use that picture as an argument of a function. So let's say I want to detect edges in that image. There's the result. And maybe I can take that image and break it up into pieces. And so on. Well, the whole symbolic structure of Mathematica means that we can manipulate an image just like we can manipulate numbers or text or formulas or whatever. So let me just give you a tiny taste of that whole symbolic language thing. So there's a simple symbolic expression. There's another one. What about this? That turns out to be a symbolic expression too, just plus of x, y. Or something like this. Again, just a symbolic expression. And there are all sorts of very powerful functions that construct and manipulate symbolic expressions in very general ways. Like here's one of my all-time favorites, nest list. It creates a sequence of nested functions. And you can do all kinds of things with it. Like let's say the function puts a frame around things. There's the result we get from that. Or let's say we build up a user interface in a kind of nested way. This is just a toy, but you can build up any user interface programmatically like this. And you can build up very real versions very easily. But okay, let's go back to the story of Mathematica. So there it was, June 23rd, 1988, Mathematica version 1 was released. And you know, back then, even people like scientists and engineers almost never did their own computing. There were sort of specialized computer people who did that, because computing was sort of messy and time-consuming. Well, Mathematica has grown immensely over the years, but even Mathematica 1 already had the basic feel of what we now know and love as Mathematica. And back in 1988, I think for most people it was something pretty spectacular. It transformed computing into something that you could actually do without being a special, highly trained computer person. And the first big set of people who rushed in to use Mathematica were around mathematics and the physical sciences. Though even from the very beginning, there were people from a huge range of fields, sometimes quite unexpected ones. And over the years, a really, really impressive set of things have happened in the world as a result of Mathematica. For me, it's extremely satisfying, feeling that the work we've done has contributed to so many discoveries, so many inventions, so much stuff getting built. So many people telling me that they couldn't have got their education, they couldn't have done their projects, they couldn't have launched their companies without Mathematica. You know, at the beginning, it was a challenging thing explaining what Mathematica is. It's a system for doing everything computational you'll ever want. It's a language for representing everything computational. It's something that there aren't really words to describe. Well, at the beginning, the obvious killer app for Mathematica was mathematics. And so we decided, actually as it happens, it was Steve Jobs who really encouraged me in this direction, to call Mathematica Mathematica and to say that it was a system for doing mathematics by computer. Well, people got that idea and started using it and doing wonderful things with it. Now, of course, there was a lot more to Mathematica than math, even then, and even in the broadest sense of the term mathematics gets used. And indeed, over the years, even though Mathematica is incredibly widely used in math, that represents a tinier and tinier fraction of all Mathematica usage. You know, after 25 years, you might think that any software system would have kind of run its course, but not Mathematica. Instead, if you plot the growth of functionality of Mathematica, it's actually been speeding up. I always find it kind of neat. Occasionally I'll unearth the Mathematica program that I wrote 20 plus years ago for Mathematica version 1, and I'll start it up in nowadays Mathematica 8, and it'll just run. And what's more, the program will look completely modern. It's just pure, timeless symbolic programming. Well, that's what one gets for having set up the right foundations, that one can just go on building and building more and more on top of them. Well, over the years, we've built up a large and impressive team working on Mathematica, and we've invented an amazing amount of technology, an amazing number of algorithms, and so on. But one thing I've personally always been very involved in is figuring out the overall design of the Mathematica system, how all the functions in it should look to the user, how they should fit together, and so on. It's actually very hard work, but it's a fascinating process. I mean, really understanding at a deep level all these different areas to be able to create the right structures, the right functions for them. You know, the way I see the job of the language designer is this. There are all these computations out there that people might want to do. You have to understand this whole space and see what the right primitives are from which these computations can conveniently be built up. And then you give these names to those primitives and you implement them. And those become the functions and the other constructs in the language. You know, in a sense, it's a big responsibility being a language designer, because when people learn your language well, they're not just using it, they're actually thinking in it. And in Mathematica, it's really neat to see people who know the language well. They're so incredibly fast to implement incredibly impressive things. Now, of course, in Mathematica, there's sort of an unfair advantage, because in addition to the idea of symbolic programming, which is what lets Mathematica be such a high-level language, there's another point. Mathematica has an incredible amount of algorithmic knowledge built in. One of our goals with Mathematica has been to build in essentially every general algorithm one can imagine, in every area. Numerical computation, image processing, data analysis, graph theory, whatever. And that means that right there in the language you can call on any of these things. It's sort of just free inside your program to solve a traveling salesman problem, or do elaborate image processing, or diagonalize a giant sparse matrix. And all this stuff is completely integrated in a coherent way into the core system. You're not chasing libraries or buying random toolboxes, or trying to glue together all sorts of bits and pieces and hoping they'll work. You have all this functionality, all these algorithms built right into Mathematica, all arranged to be consistent and coherent. You know, it's interesting. When we attack a new area, it's an interesting process. We're always building for the long term, implementing in a very clean way everything that can reasonably be implemented. Usually we have to invent a lot of stuff. We figure out how to represent things in the most clean and coherent way, and that'll usually reveal holes where we have to invent completely new algorithms. And then we'll start automating things. And actually some of our most complex algorithms are ones we invent to make all that automation work smoothly and reliably. when you use Mathematica, one of the great things is how scalable it is. I mean, you can start off just doing a line at a time, calculating, exploring something, but then you can start building little functions, making little user interfaces, maybe running stuff in parallel or on GPUs or whatever. But you can just go on building. Serious large-scale Mathematica programmers tend to switch at some point to the Wolfram Workbench IDE, but the whole Mathematica system just scales right on up. And Wolfram Alpha, for example, is now a pretty big program by anyone's standards. 15 million lines, actually, of pure Mathematica code, running in production on zillions of parallel machines. And you know, Mathematica itself is now mostly written in the Mathematica language. And it's been pretty exciting, particularly these last few years, watching how much the rate of Mathematica development has been accelerating. We've got these principles of coherence and automation, and we've invested a huge amount in them. And in addition to benefiting all our users over these years, they're also now paying this incredible dividend for us, because they're letting us build Mathematica faster and faster. Like in Mathematica 8, we added symbolic probability computations, and I think we did something really nice there. But what made it possible is that we could take for granted everything else in Mathematica, the calculus, the numerics, the computational geometry, whatever. We can build faster and faster because we're constantly creating bigger and bigger building blocks, which all fit together. So that now Mathematica has, by a huge margin, the world's largest collection of built-in algorithms all integrated together and being used every day by a huge collection of people at the front lines of R&D in essentially every industry, in every technical field, in essentially every Fortune 500 company, in every major university around the world, and in lots of unexpected places. You know, it's been interesting. With its foundation in symbolic programming and its core principles, Mathematica defines a whole way to think about computing. And as the years have gone by, we've gradually understood more and more just what the implications of that are and what can be built on those foundations. Occasionally there have been some big jumps, like in the mid-1990s when we first introduced symbolic documents, or in 2007 when we introduced dynamic interactivity and functions like manipulate that provided a whole new paradigm for interacting with Mathematica, being able not just to get static results, but instantly to use the symbolic power of Mathematica to generate dynamic programs as results. You know, as I mentioned, I personally had sort of a selfish reason for wanting to build Mathematica in the first place. I wanted to use it. And actually, starting quite soon after Mathematica was first released, I was able to do that in a big way. I kind of viewed Mathematica as sort of a computational analog of a telescope, but instead of peering into the astronomical universe, I was looking into the computational universe, doing experiments with Mathematica to find out how programs out there in the computational universe behave. Well, I discovered some really, really interesting and surprising things that I wrote a big book about called A New Kind of Science. And in addition to what the book had to say about science, it also suggested new ways to create technology, to create algorithms, new ways to think about computation. And for a start, this has given us new ways to develop Mathematica. But actually, it's also given us something else, because it gave me the paradigmatic basis for Wolfram Alpha. I had long thought about trying to take the world's knowledge and make it computable. But a few years ago, building on ideas from my science, as well as on the practical capabilities of Mathematica, I set about building what has become Wolfram Alpha. So for those of you who haven't seen it, it lives on the web and in apps and embedded in an increasing range of places. Let me show it to you on the web. Let's start with something easy. Okay, that's good. Well, okay, Wolfram Alpha has tons of knowledge about the world. We can just ask it questions in natural language. And it'll compute the answer. It's got all kinds of data on all kinds of things. Let's try something education related, for example. Or let's compare two names. It's really remarkable how much knowledge in the world is computable. Here, for example, we can take birth curves, convolve them with mortality curves, figure out the most common age for people with that name, and so on. Wolfram Alpha has lots of real-time data coming in as well. Like, let's ask it the flights overhead here. There are their positions. Let's pick one of these. And there we see its route and all sorts of detailed data about its position and speed and so on. Let's try something completely different. Let's type in something like this, which Wolfram Alpha will assume is a base pair sequence, and then go and look up matches to that sequence on the human genome. Or let's try a more elaborate physics calculation. And get the answer right here in Wolfram Alpha. The basic idea is always the same. You type in a query just in ordinary natural language, and Wolfram Alpha will use all the knowledge it has built into it to compute an answer to your query. Underneath, it's an incredibly complicated system with data and models and algorithms from thousands of different domains, and a way based on some pretty major breakthroughs that we made for understanding free-form input that people give. Underneath, as I said before, it's all Mathematica, just a big Mathematica system. Well, there's a lot of exciting stuff going on with Wolfram Alpha. Let me show you one thing, how Wolfram Alpha gets plugged into Mathematica. Normally, Mathematica is a precise language that lets you build up arbitrarily large programs in a very careful way. But what if you put Wolfram Alpha into it? Well, here's how it works. Starting last year with Mathematica 8, you can use Wolfram Alpha to give free-form input to Mathematica. So you can just ask for a plot like this, and Wolfram Alpha can translate that kind of vague English input into precise Mathematica. Or we can go ahead and ask Mathematica through Wolfram Alpha to add a purple frame to that picture. Again, we get Mathematica code synthesized right from our free-form input. Or let's do some image processing. There's the result. Or we can do things with data too. There's a list of countries in South America. Or let's say we ask for flags. There's the result. Now we can use a Mathematica function to just do edge detection on those images. It's great when you know how to write Mathematica in the full language of Mathematica, but this free-form input mechanism means you don't have to know the Mathematica language. You can just get started using Mathematica knowing only plain English. It's sort of another kind of automation. You just say what you want, and Mathematica figures out how to do it. You know, with Mathematica and now with Wolfram Alpha, we have a pretty amazing stack of technology. And right now we're just having a fantastic time understanding the implications of it all and building some remarkable new products. You might have seen the 25 mobile apps that we brought out, or the best-selling ebooks that our spin-off company Touch Press has created using a Mathematica production pipeline. And in the coming months, you'll be seeing some really remarkable products emerging that build on both Mathematica and Wolfram Alpha and combine them in very interesting ways. Products that I'm not embarrassed one bit have taken 25 years of technology development to produce. By the way, I should mention a major product and direction that just came out a couple of months ago, CDF, the computable document format. It's yet another of those ideas that's made possible by the symbolic nature of Mathematica. Computable documents. It used to be the case that to make serious interactive content, you really didn't have any choice but to do all sorts of messy interface programming. But in Mathematica, we've always had what we call the notebook interface, in which everything you do is in a document that, like everything in Mathematica, can be manipulated symbolically. And using dynamic interactivity in Mathematica, we launched what we call the Wolfram Demonstrations Project, to which more than 7,000 demonstrations have been contributed to date. All underneath written in Mathematica, and all acting like little apps embedded in documents. The demonstrations project is a great source of example code, supplementing the many hundreds of thousands of examples in the Mathematica documentation system. But now what CDF does is to provide a way to package interactive computable documents so they can occur anywhere, in a web page, wherever. You can use them to make a new generation of textbooks and other educational material. A lot of work is going on in that. And you can use them to make interactive reports, which I have to say are pretty spectacular. I mean, I insisted a while ago that all the reports inside our company get generated as CDFs, and it's really amazing how much more powerful it is to be able to interact dynamically with a report and recompute what you want. And of course there's more unification, because now Wolfram Alpha can generate CDF. So in effect one's going straight from free-form natural language to interactive programs. It's just a typical example of what's possible with all this technology we have that fits together so well. I have to say that even though I originally created Mathematica 25 years ago, I'm just constantly amazed at all the things it makes possible here and now. For me, and for all of us at Wolfram Research, Mathematica has become not just a software system, but a whole way of thinking about computing. You know, outside the company, I often run into people who tell me that they're doing this or that project. And I say, well, you really should be using Mathematica for that. And they say, really? Then they actually try it, and I hear back from them. Wow, I had no idea that could work. I had no idea anything could do that. And to me, as a system designer, often what happened is pretty satisfying. They just tried the obvious thing, the most clean and direct way of attacking their project in Mathematica, and it just worked. And they were able to go all the way from beginning to end just using Mathematica. Well, I think I should wrap up here. I hope through today you'll have a chance to learn a little bit more about Mathematica for yourself. We're very proud of Mathematica and of what so many people have been able to do with Mathematica over the years. Though I have to say, you haven't seen anything yet. Thanks very much.